Okay, so in the last hour we already see the mathematical equation for simple linear regression, right? It's really very simple, right? It's just y equal to v0 plus b1 and x1, okay? So, and we know that given this model, if I know x, I can estimate the y, and the estimation is called y hat, right? And we know that the estimation would not exactly be the same as y, right? So the difference between the two is called residual, right? If we draw this equation on a plane, we will see a straight line, okay, where v0 and v1 is the intercept and slope respectively, okay? And then we will see that there are some difference between the actual data point and the line. That difference is called the residual. Okay, okay. Now here comes the problem. Where the B0 and B1 come from? Okay, we have a bunch of data, right? We have a lot of data points. So we need a tool, right, to help us find the B0 and B1, isn't it? And that is not a problem at all. In R, we actually have a function call, right? You do a function call, then you get the V0 and V1. Okay, so let's do it in some real data. Okay. What happened? So our code would be under 09 regression. You could download the zip file, right? It's just and let's start with unit 9A. Okay. So again, we have some formatting code, package, and also here is the data, right? Here's the data. So we basically run to this point. You go into the RMD and run to this point, right? Fitting the model, before fitting the model. So you already have the data, right? So before that, it's actually just preparing the data. So you just push this button, okay? Then you should have a data frame called W. This is the wholesaler's data. That's why I name it as W, okay? The wholesaler's data, as you remember. So there are 440 retailers, and this retailer are customer of this wholesaler, right? Okay, so and these are the these are the buying amount of different type of grocery, right? Average buying amount for fresh, for milk, for grocery, the type of things, right? So the data looks like, if you click here, you'll see that this is the data, right? So for every retailer, it is the amounts of fresh, the amounts of milk, amounts of grocery, that type of things, right? So for simple linear regression, the R function code is like, just look like this. This is called linear model, okay? The LM function code is R's built-in function to build linear regression, okay? For linear regression, simple and multiple linear regression, we just use this LM built-in function, okay? So what you need to put inside the LM function code, there are two things. First of all, the data frame, right? You want to know the data frame. The second thing, you need to specify the target and the regressor, right? You need to specify the X and Y. And in our case, we only have one X, right? So if we want to predict milk by grocery, okay? That's what we was. We put our target, we put our Y before the tilde, and we put our regressor, put our X after the tilde, okay? That's what we call a model spec, the model specification, okay? So you have the data, and you call this LM function code, and just tell the function that we want to use grocery to predict milk, okay? That's all. And after you call this function, after I execute this block, you will see a object called MD, right? Short for model. It can be whatever name you name it, right? But as I told you, right, in R, in the right-hand side of the equal sign is actually an expression, right? The expression could be a function call, could be a lot of things, right? Could be very complicated. But whatever, this expression will be evaluated into an object, right? Whatever is in the right-hand side of the equal sign in R would be evaluated as an object. And you can name the object whatever name you want it to be, okay? So in this case, we name it MD, right? So you use this function call to turn this data frame into a model, right? So this is a model. MD, a model is an object by itself, okay? Okay. And if we take a summary of the model, you will see a lot of things, okay? You will see a lot of things. Let's go to the notebooks for easier. So we build the model by this line of code, right? Then we can see the summary of the model. The most important thing that we want to know is the B0 and B1, right? You remember this, right? This is the general form of the simple linear regression, right? So we have the data and the tool, the method, LM, right? It's a method. The tool will help us find V0 and V1, okay? So it's something like this, okay? You have the data, right? And you put the data into a method. LM is the method, right? To help you build a model, right? So it's like a machine, right? It's like a machine. So you put your ingredients into the machine, and that machine will build a model for you, okay? So LM is not the model. LM is the method, okay? It's orange color, right? So LM is not a model, remember that. LM is kind of a method. And that method would help you, from the data, it would build a model for you, okay? And when it build a model, it actually, what we mean by build a model, well, specifically, it just find B0 and B1 for you, right? Because you already know that x and y have this relationship. What you do not know is the value of b0 and b1, isn't it? Right? So what this model do for, what this method do for you is to, given the data and model spec, it would LM, this method would estimate the b0 and b1 that minimize the residual. Okay? How it do it? It's not it's not what we can cover in our class, right? Okay? But what the LM does for us is, given the data and model spec, right? Given the data and model spec, given the data and model spec, okay? What this function LM does for us is to find B0 and B1, okay? This is the B0 and B1 that minimize the error between estimation and the actual data, okay? Let's get back to this slide. Okay, we have data W. Okay, we have the model spec, right? Right, Y and X. That's what you want to tell him. And then this method LM, there's an algorithm that, and that algorithm is to try to calculate B0 and B1, right? And that B0 and B1 would minimize, well, try to minimize the error, right? I should say residual. Try to minimize the difference between the actual value of y and actually the predicted value of y. Okay? Try to minimize the error so that the line will fit the data, right? Fit the data as well as possible, right? That's what we mean by fitting. You should hear that a lot of time, right? Fitting the model, okay? What we mean by fitting a model is trying to find a coefficients combination. This B0 and B1, we call them coefficients, okay? Coefficients. So what the method does is it try to find a set of coefficients so that the residual is minimized, right? That's what it does, okay? And that is automatically already built in LM function. We don't have to worry about that, okay? So in R, as a user of R, we simply call the function, right? And then we will get the model automatically. See? So building model is easy, isn't it? Right? As long as you can prepare the data, building model is like just one function call, okay? And after you do the function call, you can use the summary. The summary will dump out a lot of things. I'll explain that later. Don't worry, okay? But for now, you only want to know B0 and B1, right? Okay? That's the two things that we get out of the model, okay? So as long as we know B0 and B1, if you have X, then you can do it like this, right? After we know B0 and B1, whatever X we have, we can do the estimation of Y, right? It's very simple, isn't it? As long as you know B0 and B1, right? So after you know that, it's very easy to calculate Y hat, okay? And as long as you know Y hat, and in the training data, right? In the sample data, you will see that the Y hat would not be the same as the actual Y, and the difference is what we call residual. Okay. Okay. So actually, we can do the exercise. In our case, right? Our Y is W milk, isn't it? Okay. And our X is W grocery, and the B0 and B1, as you can see that we can. The coefficient is actually inside the. Let me pull it down. See, the coefficient is actually, the MD, this MD object is actually a list. You see that? Okay? And coefficient is a sub-element, right? It's a sub-element within the list. It's an element within the list. So in order to get the coefficient, we simply do this, right? The MD coefficient 1, MD coefficient 2, right? Okay? So this is B0 and B1. So we have X, Y, we have B0 and B1. So if we want to calculate Y hat, we just use this equation, right? The Y hat is equal to B0 plus B1 times X. Okay? Now at this point, X is a vector, right? How long is a vector? X is a vector, right? Isn't it? So how long is the vector X? You can see it here, right? If you can you follow me? Okay. It's 440, right? Isn't it? Okay, right? So so if X is a vector of 440, how long is Y hat? The length of Y hat is like how many? Yeah, it's also 440, right? Because R would always do the vector calculation, isn't it? Right? See, B0 and B1 is a single value, right? You see it here. Let me do it here. See, B0 is a numeric. It's a single value, right? If you type B0, sorry. It's intercept, right? And it's just, it is a single value. And B1 is also a single value, right? But X is a vector of length 440, right? So after this calculation, okay, after this line, we will also, sorry, I should do this Y hat. See, Y hat is also a vector of like 440, right? So when we calculate this, actually we don't, here we just try to do an exercise, right? We know B0, B1, and we want to use the model equation to calculate Y hat. But you don't really need to do that. Within the model, there's an element called fictive value, right? This is actually the Y hat, okay? So if you check the difference between Y hat and this fictive value, you can see that they are basically the same, right? The difference between them are like basically 0, right? Okay. So you don't really need to do that. Okay, the Y hat is already exist. It's already kept in the model object itself, right? I just do that for our learning purpose. Okay, and then we can also check the residual, right? We can see the difference between Y and Y hat, and this is the residual. Okay. And actually, the residual is actually also kept in the model object, right? So you can see that they are the same, right? Okay? So usually we don't need to do this and this because this thing is already kept in the model. I just want to show you that for learning purpose, okay? Now, the next thing we can do with the model is actually do a regression line, right? So we can plot the regression line. Actually, we want to, after we know the B0 and B1, we can actually plot the line, right? So far, we already have the data point and we already have the slope and intercept of the regression line, right? So you can make a plot, so to help us have a better understanding about linear regression, right? Okay. So in order to do that, we do a plot, okay? As I told you, like this part thing is just to set the format, right? You don't really need to do that. And this thing is, see this plot. This is the simple built-in plot function of R, right? And in this function, the first argument is x coordinate. The second function is the y coordinate. So this is the actual x and y, right? This is the actual value, isn't it? Because within the W data frame is our sample data, right? So this plot would actually plot the data point within our training data, okay? And then we want to draw a line, right? In R, there is a built-in function called f-line, okay? So if you do a f-line, and first and second argument is actually the intercept and slope, okay? Just specify the color, then you can plot the line, okay? So it's also very easy to like plot this data point and actually the regression lines in the R environment, okay? Okay. So this is actually a benefit that you do a statistic in R, right? It's very easy to verify. It's very easy to verify the model equation, right? As what we have done here. And it's also very easy to visualize what the linear regression does, right? It's very easy. The benefit of R is it's easy to verify. It's easy to visualize all of this abstract and hard to understand concept, right? Okay. Okay. So we don't. Our approach. I don't want to tell you the detail about how to do, how to evaluate B0 and B1. That's the other course, okay? In our course, we'll use LM as a tool, right? As a black box, okay? And like after the black box, we can use some R function to help us verify the model equation and visualize the regression line. That's what we have done, okay? So any question up to this point? It's okay, right? But, by the way, in Professor Li Chengxian's course, he also covered the same topic, right? He told you how to do linear regression already, right? Right?
This week they will teach the regression.
Oh, it's just starting to go into this point, right? But what kind of tool is Professor?
SPSS.
Oh, he is using SPSS. That's okay. A tool is a tool, right? Okay, tool is a tool. But in R, we have the extra benefit that after doing the model, we can play with the model, right? So make the mathematical abstract concept easier to understand. I would say so. Okay. Now this is we are using the built-in simple plotting function, right? To do the plot. Of course, we can also use ggplot, right? I do not have time to like go into the detail, but basically, what ggplot can do for us is like, as you can see, we are using ggplot, right? So in ggplot, the AES, this is x and this is y, right? Within AES, if you do not specify the argument name, right? The first position is x, the second position is y, right? So x and y and data is from W. So this is basically the same, right? And then you do the geom point, right? Okay. So this is and this is just the format of the point, okay? And that would plot all of the data point, isn't it? Okay. And then now, the one thing that we want to know is this geom smooth, okay? In ggplot, there is a function called geom smooth, and it would do the linear regression model for us automatically, okay? So you don't need to give them, give ggplot you don't need to give it the MD object, okay? You simply give ggplot the data point, and ggplot will do a LM for us, okay? Do a LM for us. So, and as you can see here, that it actually will draw a regression line, right? Okay? And besides the regression line, it will also evaluate the 95% confidence interval, okay, for the regression line, okay? You know what is the confidence interval, right? Okay? Do I need to like explain more about the you know it already, right? You know that in statistics there are two kinds of estimation, right? Point estimation and also interval estimation, right? Okay? So for the regression line is the point estimation, right? But statistics always come with uncertainty, right? So we know that the point estimation is not exactly the truth, right? There are some uncertainty come along the point estimation. So we want to know the interval estimation, right? At certain confidence. So in the 95% confidence label, the y bar is in this gray area. Okay. So the one benefit that using ggplot is actually would, besides the point estimation, it also give us the interval estimation, the 95% confidence interval. Okay. Now there's a question. If it was the 95% confidence interval, then 95% of this point should stay in the gray area, isn't it? What is the confidence interval mean? It means that 95% of time, right? The data should be within the interval estimation, right? But if you look into the actual plot, it doesn't seem that way, right? Okay? So actually most of the data points it's like out of the 95%, right? So why does it happen? Okay? Well, the point is actually what linear regression estimate is y bar. It is not y, okay? Actually, it is the 95 confidence interval of y bar given x. What y bar mean is the average of y, okay? So let's zoom in so we can see it better, okay? So we can see that in every x, right? In every given x, there are a lot of y, right? Okay? So, this actually make it worse. Okay? So, we saw that at every given x, there are a lot of y, right? So, the y hat, what the y hat estimate is not every individual y. It is the average of the y's, okay? So, so actually for example, at this point, right? It is not estimate the the 95% interval is not the 95% interval of y, it's the 95% interval of y bar. Okay? You get me? So that 95% interval is for the average of y. It's not for every individual y. You get me? Okay? So it's actually in R we can see. I'll cover the code later. Actually, you can plot the 95% interval of y. Okay, in R we can do that. Okay, so this is the 95%. The pink dashed line is actually the 95% confidence interval of y, of individual y. Okay, so you can see that like 95% of y actually stay within the pink area, right? You can see that, right? Okay. So that is one important thing. If we want to do if you want to know the uncertainty that comes with linear regression will give you a point estimation, right? But it will also tell you uncertainty that come along with that point estimation. Okay, and usually when you say the 95% confidence interval, you are talking about the 95% confidence interval of y bar. It is not 95% confidence interval of y. Okay. It actually named it differently. In R, we can do the prediction like this. Okay. Let's see how we go to this point, right? That's the next thing that I want to cover. The thing is, like, if we want to do prediction, we need new data, right? Let's go back to here. Remember this? So far, this is what we do. What we have done, right? What we have done. We have X, we have Y. We build a model from this X and Y, right? But for this Y, we already know it, right? The reason that we want to build a model is because that we have some new data, and we do not know the Y of this new data, right? Otherwise, you don't need to build a model at all, isn't it? Right? The reason that you build this model with this data is because you have some data that you know X, but you do not know Y, right? So that's why you want to build a model. Okay? So before you do the prediction, you need to have some new data, right? You need to have some new data that you know X, and you want to use the model to predict the Y for us. Okay? So and so here we are building some new data, right? We put a new data frame, okay? Table is the same as data frame, just short name of data frame. You can think it that way, okay? Table is like dplyer's data frame, okay? In dplyer, you call it table. So basically, you just treat it as data frame. So I create a new data frame, and there is only one column in this data frame called grocery, which is our X, right? You need some new X, so you can use the model to predict the Y that associate with this X, right? This is what I want to know, right? When grocery equal to 1.5, 2, what is the estimated milk, right? That's what I want to do. So I create a new data, okay, and call it just new data, right? Then I can do the estimation, okay? I do prediction, and I give it the model, and I give it the new data, right? Then I will get the point estimation, okay? If I call predict is also a built-in function in R, right? It give it a model and give it the new data, and then it will return a vector of y hat. Okay? You get me? There's a built-in function called predict. Okay? So you call predict and give it the model. This is the model object, right? And you give it a set of new data, right? And the x, in the new data, there's a column. There's a columns of x, right? And so you would use this model and use this new data to predict the y hat that corresponding to that associated with the new x. Okay, right? So this is the y hat that associated with this new data. Okay, and also in this predict, it can. I told you that besides the point estimation, it can actually give us interval estimation, right? So you can actually, if you add the argument called interval equal to confidence, it would also estimate the upper and lower bound of the 95% confidence interval. And remember that confidence interval is actually the confidence interval of y bar, okay? It is not the confidence interval of individual y, okay? If you want to know the, sorry, I do it wrong, okay? So this should be y, okay? I should make some change here. Actually, you can change it yourself. Go to your RMD and this is y instead of y bar, right? Just copy and paste, and like I forget to like remove the bar. Okay, so and you can knit it again actually. Should be very quick, right? So if you want to know the 95% confidence interval of individual y, you will need to use interval equal to prediction. See that? See the difference? Here is the, for 95% of y bar, you are using interval equal to confidence. For 95% of y itself, for individual y, you will need to use interval equal to prediction, right? Confidence and prediction, right? This is different, right? So if you want to know the uncertainty of the linear regression, when you do the prediction, you need to put in the interval, okay? That is important, okay? That is important. Well, for the rest of the course, we will basically concentrate on the point estimation, okay? Actually, for most of the managerial application, point estimation is good enough, unless you are working with finance, okay? Because the finance people, they care about risk more than every other discipline, right? Okay, so unless you are doing finance, actually the point estimation is good enough, okay? But if you are going into the finance, if you are a financial guy, if you are doing managerial finance, then you need to know how to estimate the confidence interval for y bar and individual y, okay? And this is the visualization code. I do not have time to cover them, okay? So, okay. Now, is any question up to this point of time? Okay, no question. Let's move forward, let's take a closer look at the model summary. Okay. Up to this point, we only see the B0 and B1, right? But there are a lot of information within the summary, as you can see, right? So let's take a closer look at the summary. Right? So in the beginning of the summary, it's actually the model spec itself, right? Tell you that the formula is this is y, this is x. There's only one x in simple regression, right? Data is w, and here it gives you the residuals, right? So do we have some gifts to give out today? Okay, so what is residual? Anyone? What is residual? Does anyone want to try? Just what is residual? Say louder, please. Yeah.
The difference between predicted value and real value.
Right. The difference between the actual value and the estimate value, right? Okay. And when we say that the difference between actual value and estimate value, it means that we know them both. We know both of the estimation and the actual, right? It means that within your training data, right, the residual, it only exists, right? Can only exist when you are doing with this like training data, isn't it, right? Because in the training data you have the y already, right? So you take the difference between y and y hat, which is the estimate of y. And that difference is called residual of the model, okay? So, where is that? So it will tell you the distribution. You can see that this is not, residual is not a single point, isn't it, right? Residual is a vector, right? So, every point has a different residual. At this point, the residual is very small. And this point, the residual is very large, right? Okay? So theoretically, the residual should be normal distribution. Should be a normal distribution with mean equal to 0, okay? I mean, theoretically, the mean of residual should be 0, okay? So as you can see that it do not tell you the mean, right? So there's no need to tell the mean. In linear regression, the means of residual is always 0. Okay? And in normal distribution, there are two parameters, right? They have mean, and what is the second parameter? I mean, normal distribution has two parameters, right? The first parameter is mu, right? Is the mean of the distribution. And what is the second parameter? Normal distribution, right? So has two parameters. The first thing is the middle of the distribution, isn't it? It's called the expected value of the distribution. Mathematically called mu, right? So what is the second parameter? Oh, normal distribution. Variance, right? Variance or standard deviation, right? They're basically the same thing, right? Okay? It means how the mean is actually the expected value, right? And variance and standard deviation, They're talking about how how the value spread, right? The larger the variance, the larger the standard deviation, the flatter, right, the distribution line. Okay, so it spread around. It means that the distribution, we know that center is here, but it spread a lot, right? It has a standard deviation. We can understand it simply. It's not exactly, but simply we can understand standard deviation as the average error, right? Okay, so 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 if the residual has a very large standard deviation, it's actually covered here, right? It say that the residual standard error is 0.3, okay? So somehow it's telling us that in the training data, okay, the average error between estimation and the actual value is about 0.3. Okay? Okay? So estimation is would not exactly match the actual value. Okay? So, but however, when we do the linear regression, the mean of residual would always be 0. Okay? The algorithm would guarantee that the mean residual is equal to 0. But what is different is actually the standard deviation of the residual. The larger the standard deviation, the smaller the standard deviation, the more precise, right, the prediction is, isn't it, right? So you want a small value of this because it means that the small average error, okay, of this model. So if you have a model that has a very small standard deviation on residual, then this model will do the very precise prediction, and vice versa, right? Okay, so this is a thing that we care a lot, right? When you do a model, besides the prediction, you also want to have an idea about what is the average error that this estimation, that comes with this estimation, right? Okay. So, and then there are a few things that's more difficult to understand. For example, like the R square, and also there are some standard error on the coefficients, right? There are a few things that are a little bit more complicated, but the first thing that we need to, besides the coefficient, the first thing we need to know is actually the residual standard error, right? That's the thing. And also the distribution of the residual is also important, okay? And then we would also want to know that I'll try to like explain the next thing I will try to explain is actually these things, okay? See, come with this is B0 and this is B1, right? So as you can see that when it estimates B0 and B1, it besides the point estimation, it also gives us standard error, right? So this is actually the standard error of the coefficient. Okay? So this is the standard error of y hat, right? And actually, this is the standard error of B0. And this is the standard error of B1. Okay? Okay? So the coefficient B0 and B1, they are estimated as a random variable. Okay? So what I mean by random variable is that actually it comes with a point estimation and a standard error, right? So if we plot, we can make a plot. We can actually plot the what is this 0.57 and 0.3, right? So if we use this as the mean and use this as the standard error, okay? So we can actually plot a normal distribution like this, okay? So this is the parameter B1, right? So usually we will always see the expected value of B1, which equal to this, right? But actually there are uncertainty about this B1, okay? Okay? This thing is actually just the expected value of B1. B1 also comes with some uncertainty, okay? And depends on your data, sometimes the uncertainty is large. When the uncertainty is large, you will see a widespread distribution, okay? When the uncertainty is small, then you will see that the distribution of the B1 random variable is very narrow, right? For example, like in this point, right? So if we plot the distribution of B1, it would look like this, okay? So and with its distribution, we can actually mark the 95% confidence interval B1, right? You should have learned this in like Professor Li Tenshen's course already, right? If you know the mu and also the sigma square, right? If you know the parameter of the distribution, you should be able to find out the 95% confidence interval, right? So if the 95% confidence interval do not cover 0, we will call it significant, right? Okay. Actually in our course, the significant, we do not use that concept significant too much, okay? We don't care too much about significance, okay? Especially in the realm of big data, right? We do not care too much about the significance, okay? But, well, as for completeness, right? I just need to explain what is significant and where does it come from, okay? So you don't need to like understand this part. If you do not understand it very well, it's still okay. But you should know that the coefficient actually come with the estimation of the coefficient come with uncertainty, right? Okay, and what we mean by significant is to say that we are certain that this coefficient is apart from 0. Okay? What we mean by significant, simply put, is to say that we have a higher level of confidence that this coefficient is apart from 0, right? So if it like very close to residual, if it's 95% confident it will cover 0, then this coefficient is not significant. Okay, that's what we mean by significant, and that's what I want to say about significance, and that's good enough for our course. Okay, now let's take a break and let's get back at 10 after 11. Okay. So don't worry too much about this like significant type of things, p-value type of things. We won't use it for the rest of our course, okay? We won't use it for the rest of our course. Okay, sorry. Yes.
等一下，不见了。如果，不见了。不见了。我找一下。这边。
So this is the new data, right?
这个里面这个 sequence 这边是要做，它是
Okay. Sequence is a way that we generate data. So 我现在想要，因为 new data 嘛，我要无中生有把它长出来，不是吗？所以我说 sequence is a way that we generate new data. So sequence 1 5就是说从1到5之间，那我要每0.5跳一下这样。所以它会产生一个 vector， 从1到5，然后每隔0.5跳一下的。
所以这个是 x 嘛，对不
对？对。
那如果像我看那天那个 normal distribution 里面也有 sequence， 它就跟你这个一样的概念，对不对？也是。
对 ，sequence 就是通常你就跟他讲说，我要从哪里到哪里，然后间隔多少跳一下，那这样的话它就会产生一个向量出来，这样。对嘛？就是你凭空要产生一个向量，怎么产生出来呢？如果你是要，如果你这个向量是要相同间隔的这样，那 sequence 就是在帮你产生这种相同间隔的向量。
然后还有，y bar 跟普通的 y bar 是
y bar 通常我们这个是那个几率统计的 convention， 只是他们的传统是这样写这样。y 然后那只要在这个 symbol 上面加一个 bar， 就表示是这一个变数的平均值这样。你加一个 bar 在一个 variable 上面，就表示是，因为几率统计里面那个 symbol 都是一个随机变数，不是吗？对吧？随机变数怎样呢？它值会变来变去，变来变去它有个平均值嘛。你加一个 bar 在那个 symbol 上面的话，表示说它是这个随机变数的平均值，这样。了吗？那如果是写 y， 那我指的是每一个 individual 的 y， 不是 y 的平均值，是 every individual y。You can have a lot of y, right? But no matter how many y you have, there's only a average, right? It's only a mean.
那还有这一个是 residual， 说是 the difference between the actual data and the predicted, right?
Right. It's this one.
那这个那个什么 actual data 跟 predicted 的 formula 是一样吗？还是如果 actual 就没有再用 formula？
Is that again?
那个因为
这个是 residual 的分布。
The difference of your predicted data and your actual data, right? 那我们用 predicted data 就是刚刚的那个formula，对不对 ？y 等于什么什么
Right. This is the predicted data. We actually would not say that predicted data. It is the predicted y, right?
有方法把它算出，就是有一个 formula 嘛，像我们刚刚用那个。
有啊，刚刚不是有讲说，我好像好不见了，等一下。糟了，我的滑鼠跑去哪里？
没电。
不是，它好像被，不会吧？
没电。
这样还蛮惨的。我的滑鼠不会 work 了，不知道为什么。我觉得我，
不好意思，它闪了一下，不见了。
因为我觉得好像是什么卡住了。 觉得好像糟了。OK， 好像有点恢复正常，刚好像是那个 PowerPoint 当掉了。好，那
这个是那个我们用来算 prediction 的那个 formula。
对啊，那个 prediction 的话，我们会用这个指令来做 prediction， 对吧？我说，对，用这个 predict 来做 prediction，对吧？你不是真的需要自己这样子去算你的 y，
就是这样子。
对啊，我说这是它的 model formula，right？但是as long as 你已经有一个 model 在这里，其实你并不需要真的自己这样去算，这样。对，你只要直接把这个 model 跟 new data， 然后去扣这个叫 predict， 其实它回来的就是那个 y hat。
那如果 actual data 的话，就是直接给我们的 data， 那个就不用算。
对，那个 data is already， it's already， 不是有一个 W 吗？你的 W 怎么不见了？啊，在这里呀。那 actual 的 y 就已经在这里了嘛，对吧？哦，因为你一开始 build 那个 model 的时候，不是就已经有一个 y 了吗？这里看不到的，因为你现在看到的这个，你现在看到的这些东西是在这里，对吧？这些东西它其实是，这个是那个 estimate value， 就是它的点估计，我们说的。然后这个的话是它的区间估计，这样。OK。
所以这一个 formula 是你的自己 prediction 的那一
个。这个 formula 是 predict y hat。然后你如果加了 interval 的话，它就会做 y bar 的 confidence。那你如果加这样的话，它就是会做 y 的 95% interval confidence。
可是都是 prediction。
对，他们都是 prediction。这个东西都是 prediction。
只是说一个是 y bar， 一个不是 y bar 这样而已。
对，其实 y bar 跟 y 的 prediction point estimation 是一样的，对不对？但是他们的 interval， 他们的那个 uncertainty 是不一样的，对不对？是吗？所以 like that's why you have like 这里面这个黄色的部分是 y bar 的那个区间估计，然后这个粉红色之间呢，它是 y 的区间估计的，right？ OK。Okay, let's get back.